So the previous video, I went over the basics of oxidation reduction, where oxidation involves the loss of electrons, reduction is the gain of electrons. So this video here is going to focus on a couple different types of oxidation reduction reactions, specifically combustion reactions, synthesis reactions, and a little bit about decomposition reactions. So the first type of reaction is called a combustion reaction. Combustion involves the burning of something in the presence of oxygen. So in this case here, we have hydrogen gas being combusted with oxygen gas to produce water. Notice the oxidation state of hydrogen is 0. The oxidation state of oxygen is 0. And for the case of water, even though this molecule is not ionic, I will pretend it is ionic for purposes of this illustration. So oxygen have a charge, it's in group 6, so it would be a charge of -2. Hydrogen is in group 1, be a charge of +1. Since there's 2 H's, that would make the negative 2 cancel out. Now, oxidation states are just a bookkeeping method of keeping track of electron flow. These are not real charges. As you can see, hydrogen has an oxidation state of 0, and it becomes +1. Oxygen has an oxidation state of 0, and it becomes -2. So hydrogen is going from 0 to +1. So since it became positive, it means it lost electrons. Hydrogen was oxidized. Oxygen was reduced. Reduction is the gain of electrons. O went from 0 to -2. It gained electrons. That is reduction. Therefore, oxygen is the oxidizing agent. The oxidizing agent gets reduced. H2 is the H is the it was oxidized. Therefore, H2 is the reducing agent. Here's some more combustion reactions. CH4 plus O2 was done on I already did that on a prior video, so I'll jump to C8 H18 plus O2. The combustion of hydrocarbons. Whenever a hydrocarbon is combusted, we always make CO2 and water. CO2 and water. So this is also a big example of redox. If you look at just the oxygen portion, oxygen on the left side has an oxidation state of 0. On the right side is -2 for both those. Let's see, carbon and H. H is +1. H is the oxidation state of +1. There's 18 of those, so it's actually essentially like saying +18. Carbon would have to be, there's 8 carbons, so it's basically like saying 8x equals 18. Solve for x. X equals 18 over 8. Divide these by 2, we get 9/4. So each carbon would have an oxidation state of -9/4. That's unusual, but that's what it would be in this case. The oxidation state of carbon is -9/4. On the right-hand side, carbon over here would be a +4. And H, of course, is +1. So H is not changing. H remains +1. Carbon is changing from -9/4 to +4. O is changing from 0 to -2. If you have any questions on how I got this figured out, let me know. The point here is that this is, since oxidation states are changing, this is a redox equation, or redox reaction. Now, as far as balancing this, we always start with C, then H, and then O. So on the left-hand side, we have 8 carbons. I have 8 carbons on the left. I have 1 carbon on the right, so if I put 8 in front of CO2, check the hydrogens. 18 on the left, 2 on the right, so 2 times 9 is 18. Now we check the O's. 8 times 2 is 16, plus 9 more O's. That's a total of 25 oxygens. I have 2 on the left-hand side. 25 is an odd number. Therefore, I know I'm going to have 25 O2s, and I'm going to double the rest. 2, 8 becomes 16, 9 becomes 18. So the coefficients are 2, 25, 16, 18. The last one, done the same kind of way. C2H2 plus O2 makes CO2 plus H2O. Balance that. Carbons first. 2 carbons on the left. 2 H's on the left. I've already got 2 H's on the left. On the right. I have 2 times 2 is 4, plus 1 more. That's 5 O's on the right, 2 on the left. Again, since this is odd, we're going to need to put 5 in front of O2 and double the rest. So it'll be 2 in front of C2H2. 4 will now be in front of CO2. And 2 in front of water. Now it's balanced. Combustion can also involve the combustion of a hydrocarbon derivative. This happens to be called what's known as an alcohol. This is ethanol. Alcohols have an OH on the end of them. The point is, though, when you burn this in the presence of oxygen gas, you're still going to make CO2 and water. Alright, synthesis reactions. Synthesis reactions involve the combination typically of elements to make something more complicated. They're the general form of A plus B makes AB. So here's an example. Sodium metal reacting with chlorine gas to make sodium chloride. If you check the oxidation states, sodium metal, 0 charge. Any element in any element would be 0. Chlorine gas, 0. Now chloride ions, -1. Sodium cations, +1. Sodium is going from 0 to +1. Chlorine going from 0 to -1. So sodium is losing electrons to become positive. Chlorine is gaining electrons to become negative. So losing electrons is oxidation. Gaining electrons is reduction. So this is indeed redox. These are more similar examples. Sodium with oxygen gas to make sodium oxide. Sodium, and as you can see here, as far as charges, Na is +1, O is -2, so you need 2 sodiums, and to balance the equation. This is review from Chem 1025. More similar examples. Sulfur is interesting. Sulfur can exist in different forms. One common form of sulfur is S8. So to balance that one, to balance that one. 8 sulfurs on the left, 1 sulfur on the right. So put 8 in front of the SO2. 8 times 2 is 16 O's on the right. Therefore, 8 O's need 8 oxygen gas molecules on the left. Now the Fe plus O2 makes Fe3O4. Let's take a look at the charge. Check the oxidation states here. Iron metal by itself is 0. Oxygen gas by itself is 0. And again, free elements are always 0. This iron oxide, oxygen is in group 6 of the periodic table. Therefore, oxygen is -2. -2 times 4 is -8. We have 3 irons. So 3x has to equal 8. Therefore, x equals 8 over 3. So the oxidation state of iron is 8/3. And positive 8/3. So iron is going from 0 to positive 8/3. O is going from 0 to -2. As you can see here, we have a chain electron transfer. Oxygen is acquiring electrons. That is reduction. Iron is going from 0 to a positive oxidation state. If it goes from 0 to something positive, it is oxidation. Oxidation is loss of electrons. The species involving oxidation, since iron is being oxidized, iron is the reducing agent. Oxygen, therefore, is the oxidizing agent. The oxidizing agent gets reduced, the reducing agent gets oxidized. So that's that. As far as balancing is concerned, I have 3 irons on the left, 1 iron on the 3 on the right, 1 on the left. I have 2 O's, 4 O's. So I'll put a 3 here and a 2 there, and of course the last one, the iron oxide, is 1. I have to be a little careful about problems like these. As we know, iron is a type 2 metal, so iron could also have formed just FeO, or it could have formed Fe2O3. So these would be the 2 most common situations. This one here is Fe3O4 is most likely a combination of iron 1 and iron 2. This metal ore here, it could be an alloy, or it's a mixture of different iron compounds together. But this ends up being the overall result of what you get. Okay. Decomposition reactions. So decomposition reactions are similar to synthesis, but they're kind of like the reverse. So imagine AB breaking down to A plus B in some fashion. In other words, one reactant is breaking down into multiple products. So the decomposition of water into its elements. The decomposition of mercury 2 oxide into its elements. And likewise sodium chloride. Again, these are redox. The elements on the right-hand side, all these have 0 oxidation state. 0, 0, 0, 0, 0, 0. These are all elements in the natural state. They're all 0. The right side, for example, the mercury 2 oxide, oxygen's a -2, mercury's a +2. So mercury's going from +2 to 0, oxygen from -2 to 0. Again, we have a change in oxidation state. These here are a review from Chem 1025. These examples here, at least when I teach the class, these are review. These examples. The decomposition of metal perchlorates and metal chlorates. So metal perchlorate is a metal with ClO4 with some particular subscript, and metal chlorate is MClO3 with some particular subscript. Recall that chlorate and perchlorate have a charge of -1. ClO4 -1, ClO3 -1. So the number of these that we need, the number of chlorates and perchlorates needed, will correspond to the charge of the metal. So when metal chlorates or perchlorates decompose, you're going to make the metal chloride. So the metal is going to combine with the halide. So this chlorine actually also could be a bromine as well. So it could be metal bromate or perbromate. These examples all involve chlorine. So K is going to combine with Cl to make KCl plus oxygen gas. You have to memorize this. You need to simply know that. If you see a decomposition reaction involving ClO4 or ClO3, BrO4, BrO3, and it makes no difference, this is what's going to happen. When you balance this, we have 3 O's on the left, 2 O's on the right. The lowest common multiple of 2 and 3 is 6. Therefore, I put a 2 in front of KCl. Sorry, 2 in front of KClO3, 2 in front of KCl, and we need a 3 in front of O2. 3 times 2 is 6 O's, 2 times 3 is 6 O's, 2 KCl's, 2 KCl's. Now, is this redox? Let's find out. Why is this the redox problem? So we have 2 KClO3 breaking down into 2KCl plus O2. So let's check the oxidation states here. Oxygen is -2. Potassium is in group 1 of the periodic table. It is +1. Group 1 elements are always +1. Now what about this chlorine? To figure out the chlorine, we know there's 3 oxygens, so 3 times -2, that is minus 6. 3 times -2, that is -6. You have 1 potassium. That is +1. So -6 plus 1, that is equal to -5. Now, KClO3 has got no overall charge. So the charge of potassium, sorry, the charge of chlorine has to be positive and cancel -5. Therefore, chlorine has to have an oxidation state of +5. Normally we think of halogens, chlorine, bromine, iodine, etc., have being -1, but in this case, chlorine takes on a positive charge. Look at the right-hand side. Cl is group 7, -1. Potassium in group 1 is +1. Oxygen gas by itself, 0. So what's happening here is that K is going from +1 to +1, so K is not affected. Cl is going from +5 to +1, so it is acquiring electrons. If it came less positive, so it had to gain electrons, reduction is gain. So Cl is being reduced. Cl +5 is being reduced to Cl -1. Oxygen going from -2 to 0, that implies it had to lose electrons. If you become less negative, you lost electrons. That oxidation is lost. So oxygen is being oxidized to O2. So there we go. So it makes it, that makes this redox. Let's take a look at MgClO4 subscript 2. Magnesium combines with Cl to make MgCl2 plus O2, and we just have to balance that. There we go. Last one, AlClO3 subscript 3, AlCl3 plus O2. Recall aluminum is +3, therefore chlorine has to be -1, so we need 3 chlorides. Now to balance this one, we have 9 O's on the left, 2 O's on the right. So what's the lowest common multiple between 2 and 9? That's 18. So if I put a 2 here, a 2 in front of AlClO3 subscript 3, if I put a 2 in front of aluminum chloride, and then 9 in front of O2, that should work. And there we go. That's how you balance that one. The remaining decomposition reactions involve new material that you may not have seen in Chem 1025, so that will be part of a separate video.